everyone, and welcome back to our series on exploring neutrinos at the college level. Last time we left off with what I hope was quite the cliffhanger, the uncertainty in the number of scoops of ice cream in a sample. For neutrinos, this translates to a simultaneous combination of neutrino mass states, something that we would call superposition in quantum mechanics. Before we truly uncover the incredible consequences of this superposition, though, let's first focus in on how just one neutrino mass state changes in time as it propagates through space. Up until now, we've used ice cream shops, flavors, and scoops as analogies for the processes that create neutrinos, the neutrino flavor states, and the neutrino mass states. There's something fun about one of these processes that we should probably acknowledge, and it's the process of beta decay, the breaking down of matter, spitting out particles, including the electron neutrino. Story time. Back in the early 1900s, there was a problem with this process of beta decay, namely a problem with energy conservation, momentum conservation, angular momentum conservation. What a beautiful combination of issues. This is when Wolfgang Pauli came around and said, hey, we could fix these problems if there was a new particle, one without electric charge, and one that's pretty tiny. From this, the neutrino was first postulated. Except that Pauli called his particle the neutron before James Chadwick discovered the actual neutron, which was much, much bigger. And then Pauli's neutron became the neutrino. End story. Back to our ice cream shops and neutrino mass states. If we want to start understanding how neutrinos move through space, we need not look any further than the crowd pleaser of all intro physics, F equals ma. Get pumped! F equals ma can tell us something about how particle motion in general is modeled. First, let's rewrite this equation by moving m over. Okay, cool. We can then tell that an object's mass is an important player here. We can also see acceleration being important, which comes from changes in time of an object's position. On the left, the force acting on an object is often dependent on its location in space. So this side of the equation depends on something that changes with position. This all prepares us to jump into another crowd pleaser, this time, the Schrödinger equation. There are several ways in which you could write out the Schrödinger equation, and we're going to do it in a way that feels somewhat familiar. We'll find something that changes with position on the left. Here, this is a partial derivative for x. Then division by mass on that side as well, and also something that changes in time on the right. Here is another partial derivative, but for t. The main weirdness of the Schrödinger equation comes from the constants we're about to throw in, and also just the notation for neutrino mass states, which you've likely realized by now. It's the weird line, and then the name of the thing, and then the bracket thing. This is called a ket in bra-ket notation. You put those two things together, you get a bracket, or a bracket. On both sides, we'll add in the neutrino mass states the way we've been labeling them, and we're adding x and t because we care about how these states change with time and position. Last but not least, we throw in some constants that complete the picture. I hope you're seeing the parallels between these two equations. The reason we did this is because we want to know how to write down an equation for how the neutrino mass states change in time as they move through space. We'll keep comparing to our F equals ma case for guidance too. If you've ever taken intro physics, you've maybe seen this equation for the motion of a falling object near the Earth. And all the crucial ingredients are here. The position y changes in time based on the initial starting position for y at time t equals 0, and then a term that depends on time. Believe it or not, this logic will help us make sense of the equation for how neutrino mass states change over time. We'll start by writing down the mass state at some time t on the left. On the right, we'll find both of the same types of elements as we did in our falling object equation. First, we add in what the mass state was doing at time t equals 0, and then we add in a term that depends on time as well. Look at that! We've uncovered an equation of motion for a neutrino mass state. If you're curious about all the nuances that I've very conveniently glossed over in this setup, I'll soon be posting a video that goes into all these neutrino aspects, but with a ton of math. For now though, us drawing analogies to simpler equations should do. The main takeaway in this video that will become the cornerstone of oddity for neutrinos is this term that depends on time. This thing, delta, has some other quantities hidden inside. Importantly, it depends on the squared mass value of the neutrino mass state, meaning that each of the three mass states will have a different delta value because they each have a different mass. Just like the different numbers of scoops for our ice cream. In the next episode, we'll uncover what all this means for neutrino flavors. And I gotta say, ice cream has never been more mind-blowing.